Welcome to all. Now we are going to see about deadlock and virtual channels. The communication channels between nodes in a wormhole routed multi-computer network shared many possible source and destination pairs. So the physical channel, it's not enough to communicate properly. So we are in need of virtual channels. So here we are going to explain the network partition and the multicasting by avoiding possible deadlocks. So what is virtual channel? Virtual channel is a logical link between two nodes. It's formed by flit buffer in the source node, a physical channel, and a flit buffer in the receiver node. So this figure shows the four virtual channels connected by a single physical channel. Here we have four virtual channels in the source node and the destination nodes. Four flit buffers are used in the source node and the receiver node. Each node contains one flit buffer. So one source buffer is paired with one receiver buffer to form the virtual channel when the physical channel is available. When the physical channel is available, each source node is connected with each other destination node. Physical channel is used here in a time shared manner. That is, all the nodes from the source and the destination can share the physical channel in a time shared manner. When the source buffer holds a flit, it's awaiting to use the channel. When the receiver buffer holds a flit, which is just transmitted to the physical channel. So the channel is made by a wire on the fiber. Channel is purely created by a wire or the fiber. So the physical channel by virtual channel is conducted by time multiplexing on a flit by flit basis. Flit by flit basis, each node is communicated through the virtual channel. So here they are giving one example of using the deadlock situations when we are sharing virtual channels. The data may appear either in the buffer or in the channels. So there are two types of deadlock situations caused by a circular wait. So what does mean by circular wait? One node holding a resource that is not holding a resource, that resource is needed by another node. Both are not releasing their own nodes. Here they create a circular wait deadlock situation. And here figure A is an example for buffer deadlock among four nodes with store and forward routing. Store and forward routing buffer deadlock. Here we have four nodes, node A, node B, node C, node D. Each have their own packet buffer, and a circular wait situation results when the four packets occupy the four buffers in four nodes. Until one node discards a packet, the communication cannot be continued. Okay. And here they are giving one second example, which is a channel deadlock. Here they are passing at a time. Four nodes are trying to pass a message through the channel. Each message is message 1 for node B, and message 2 for node C, message 3 for node D, message 4 for node A. And the message is transmitted via individual flit, and each flit occupies the communication channel, and no more forwarding further. No one has the option to forward further. Okay, so the four flits occupy the four channels simultaneously. If any one of the channel is free, then we can avoid this cycle situation. And we can also represent this deadlock situation in a channel dependence graph. Channel dependence graph means uh, in this graph we have channels are represented by nodes and the arrows represent the dependence between the nodes. Dependence between one node to the another node. Here they are giving an example of the deadlock channel. Here we have a deadlock channel A, B, C, D, C1, C2, C3, C4, and all the channels are engaged. And here we have a deadlock situation, and this deadlock channel is represented by a channel dependence graph, and it contains a cycle. That is, C1 channel 1 is waiting for channel 2, and channel 2 is waiting to get a resource from channel 3, and channel 3 is waiting to get a resource from channel 4, and here that forms a cycle. Okay. To avoid this deadlock situation, we move on to the next step. We have to use channel multiplexing at the fleet level and the packet level. That is, virtual channels can be implemented to avoid this deadlock situation. So in figure C and D, we are going to see the how we are going to avoid this deadlock situation between the channels. Here we are introducing channel 4, sorry, two virtual channels V3 and V4. Here we using these virtual channels, the original physical channel gets free. That is C3 and C4 gets free, and the deadlock gets avoided. So the channel dependence graph for this deadlock avoidance channel is shown here. That is C1, C2, and instead of C3, C2 uses the virtual channel V3, and V3 uses the virtual channel V4. Here the cycle breaks and the deadlock gets avoided. So what is the use of using virtual channel means we can reduce the channel bandwidth, effective channel bandwidth for each request, and there is a trade-off between network throughput and the communication latency when we are using the virtual channels. And when we are using high-speed multiplexing, we are in need of a large number of virtual channels to implement the high-speed multiplexing concept.